My name is Fernanda Felipe. I am electrical electronic engineer and I'm an application engineer at TCS. As you know, reseller of MathWorks solutions in the Middle East. Today, I will be guiding you through to the digital engineering ecosystem and how it can support aerospace and defense industries challenges. Okay. Okay, before to share the agenda, I want to promote the upcoming webinars. Okay, this is the first webinar in a four-part of series. Okay, today we are focusing on digital engineering ecosystem, but I would like to show you a map to later dive in different topics. Okay, so in this first line, it will be our next event. Okay, mission engineer, focus on mission engineering, where we define overall emissions, requirements, system of systems, architecture, and validate through the simulation. Okay. And the next webinar, the third one, the platform engineer, we are focused on all of those mission engineering. Okay, mission needs are translated based into specific platforms such as aircraft, vehicles, ground vehicles, satellites, basically covering their design, simulation, and integration. Okay, and the fourth webinar. Finally, we have a very good one, by the way, focusing on hardware and software integration. So we are going to detail the implementation, development, simulation, and how deploying the hardware, how the software that we will run on those of these platforms. Okay. So we speak about software in the loop, hardware in the loop. So this is a very good and last webinar. Okay, please, I want to ask you, stay tuned to our social media channels and websites, so we'll publish all these registration details and upcoming webinars. Okay, just out of curiosity, so the next one is already confirmed in June 9th. Okay, the next one and mission engineer focus and platform we have in June 30th. Okay, so probably we have the last one in July and August. But again, please stay tuned into our social media, the LinkedIn website. Okay. Okay, so good morning, everyone. I think we have more attendees. So thank you again for joining today. Let's start talking about our space and defense industries and how this, topics are very, common and growing. So the aerospace and defense industry is undergoing a major transformation. We know. So we are seeing increasing system complexity, tighter, development timelines, and growing demand for integrated mission level capabilities. However, with this, how can I say, evolution comes a fundamental challenge. How do we design, develop, and verify highly complex systems while reducing risk, cost, and time to deployment? If you are a manager and leading teams, so you should know all these challenges, right? In today's session, we explore how organizations are addressing these challenges through a more connected and model-based approach. Okay, so we'll begin by looking to a key industry based on the trends and challenges and how they are reshaping the system development. Then we'll introduce the concept of digital thread and how virtual engineering solutions enable teams to connect to data and models and workflows across the entire life cycle. Okay. Finally, we will bring everything together with a MathWorks demonstration. Okay, this is a new demonstration, new MathWorks example. I'm excited to introduce to you where we simulate and verify a quadcopter, okay, system architecture, showing how these concepts are applied in a practice from design to validation. And by the end of this session, so you have a clear, I expected you have a clear understanding of how to move from this connected process to a fully integrated digital engineering workflow, following the digital thread approach. Okay. Um, Again, please, if you have any questions during my presentations, I have quick questions. I believe you know the answers. Please feel free to share by chat. I will be happy to discuss in the end. Okay, let's start our session speaking about the trends. Okay, according to this Industries Association vision for 2050. Some of the key technology and innovation trends in aerospace and defense will be AI, virtual reality, digitalization, and digital transformation. And how about the technology trends? So we can see this is very interesting. I love it. This how can I say, this research, so we can find exactly that we are looking for. AI, everybody knows. AI, everybody is aware about this approach. Now we have deep learning, machine learning, any types of algorithms to go through, to go into an AI approach. But when you use data and algorithms to support decision making, automation, and to be, intelligent in defense systems. So this is reality. They are using the trend, but they always try to improve this methodology. Okay. Additive manufacturing. This is another key trend for additive manufacturing or 3D printing. Okay, I don't know if you know about this, but basically it allows us to produce highly complex and lightweight components that we are not possible with the traditional methods. Okay. For advanced defense equipment, so we are talking about the high-tech integrated systems for surveillance protections, surveillance capability, protection and precision, in operations across the domains. And we need to talk about, just click and so I need to talk about the robotics and autonomous systems. This is a good key technology trend. So the machines like drones, vehicles that performance, missions and with a minimal human control. So we are always, eager to improve these autonomous systems. Immersive technology. So we talk about the VR, AR tools used for training, simulation and mission planning and realistic environment. Okay, we want to see in the real time. So in this case, we don't mind if it's this real time. It's in every second, every minute, every 24 hours. But we have this data. We have this in real time. Okay. Cybersecurity, so protects defense and based on the network systems and the data from cyber threats and attacks. So now, unfortunately, it's a reality. We need to protect our systems. And finally, we have this IOMT. I love this expression. I don't know if you are get familiar with this Internet of Military Things, but this is very interesting. So they are focused on network of connected military sensors, platforms, and systems that share the real-time data to improve situational awareness or decision making. Okay, so these are the key that my point of view interesting to share with you. Okay. In aerospace exploration, so we have NASA, or good reference in aerospace. If you're working in aerospace, we need to talk about it. They are using AI and digital twins to simulate Mars-like conditions and support space missions in the real time. Okay, this is a very interesting trend for aerospace. Now, another key trend in aerospace and defense, 100 connected to our topic in our webinar title, it's digital engineering and digital thread based on the model-based system engineering. So digital engineering, it's not just a technical upgrade. It's a business advantage. So in aerospace and defense, manufacturers gain a real-time visibility into a cost, schedule, quality, and risk. They are promising 2026 the digital engineering is evolving into a AI driving data-centric ecosystems. So what does it mean? Where the digital threads, digital twins, and platforms enable real-time predictive decision making, okay, across an entire life cycle. Okay. Before to start about our main topic, I want to ask you if you know the difference between systems engineering, digital engineering, and mission engineering. Okay, so after looking at these key trends in aerospace and defense, it's natural to make this question. Are you familiar with the system engineering, digital engineering, mission engineering? So let's take this moment and to explore how they differ and how each one fits in this industry, okay? So this is very interesting. I love to prepare this content because I learn it as well. So we always learn it, and we learn it with our customers. We learn it with our, trends that we can see every day. So let's start with system engineer, SE. Okay, basically system engineer is, I assume this is a well-known approach to manage complexity of large projects, right? It can, how can I say, it can include both hardware, software aspects, and as well other processes that are relevant to overall systems, right? Digital engineering. Digital engineering use models to simulate, right? And digital thread to design, test, and manage systems across the life cycle. Okay, so we are talking about to manage the systems across the life cycle. And how does mission engineering integrate with the system engineering, digital engineering? Okay, it evaluates how systems work together in operational scenarios to achieve a mission success. Okay, so why we are talking about mission engineering? Because it's totally fit with our, our propose here. So how aerospace and defense is looking for system engineer and digital engineer. Okay, the objective is to be there. Okay, in summary, let me add here the description. In summary, system engineer defines and builds the system. Digital engineering, we can say, enables, okay, a model-based connected life cycle, and mission engineering evaluates how those systems perform together to achieve operational outcomes. Okay. So, talking about the support for global regional standards implementation. Digital engineering in aerospace and defense is driving by DoD. I believe you all have seen this framework, okay, such as digital engineering strategy. We have some ISOs, and then codes based on the structure. They provide the structure how to create this environment, right? In our region, so the region we have companies to adopt, right? The sovereign, the mission drive, and the AI enable defense capabilities. Okay. Now, let's look to let's explore the aspects for the aerospace and defense based on the system engineering, digital engineering, and mission engineering. Let's take a look. What kind of aspects, Fernanda? So we are looking for focus, scope, methodology, and what is the objective? Okay. So for system engineering, they focus on systems. Digital engineer life cycle plus data. Mission engineer, I want to focus on my mission outcome. What is the scope based on the system engineer? Single system. Okay. Digital engineer, system plus life cycle. In the mission engineering, system of systems. What is the methodology for system engineering? Documents plus models. If you look to the methodology in digital engineering, models plus simulations. And mission engineering, what is the methodology? Scenario simulation. We want to see everything in the same scenario. How does it work? What is the objective? What is the goal using a system engineering approach? Build it correctly. Digital engineering, build efficiently. And mission engineering, achieve the mission. This is the objective. Okay. In summary, we can say the digital engineering, it's a kind of bridge, between the traditional system engineering and the mission driving operations. Okay. Take a look. Sorry, I forgot to add the mission engineering. Let's look at based on the pyramid. Okay. So we need to take a look at the foundation. Okay. We have system engineering. This is where we define requirements, design the system architecture, and ensure that we are building the system correctly. And then I want to see on top of that, so we have digital engineering, which acts exactly as an enabler. It allows us to design, to simulate, to test, and validate systems digitally before building anything physically. Okay, we want, as I remember, we want to save money. We want to save time of my engineering team. And at the top, we have mission engineering, which focus on the bigger picture here. Okay, so we are looking for the pyramid here. Does the system actually achieve mission success in the real world scenario? Okay, so I would like to use this slide and to invite you all for our next webinar, okay, in June 9th. So we intend to go deep to this mission engineer and system of system approach, okay? So let's talk about a common user challenge in system development. Okay, if you are working in system development in specific domain or a specific area, please share with us by chat if it makes sense or if you have any comments. I would love to hear from your side as well. So in system development, we have some challenges, okay? And this diagram shows common challenges, okay, in this system. So highlighting how requirements architecture, sorry, I just click, it's going. Okay, so you can see exactly, it's hard, to use. You have a steep learn curve. You need to identify, you have issues like a difficult, to handle these changes, and the lack of traceability. So this is another challenge as well. And between the systems view, so you cannot see if you're working in a system engineering team, so you cannot see what exactly the people were working from electronic for guidance and navigations or for electrical systems in different domains, what they are doing. So you were focused on a process and doing your best to process all this this system architecture, right? The process in general. And how we can create this digital thread, how we can start looking based on our challenges. So digital engineering environment with a digital thread approach is showing how stakeholders' needs are connected across the entire system lifecycle. Okay, it highlights exactly how requirements, models, implementation, what else, verification are linked in a unified flow to improve traceability, simplify complexity, and enable seamless analysis and validation. So this is the idea to use digital thread. You can say to me, Fernanda, it's easy to say. Yes, I know. It's easy to speak loud. It's not easy to apply. But you can at least started part of that and see what is the impact and slowly, promote this internally. Okay. The idea is exactly to unify it environment. Okay, to see the possible issues, possible integrations, everything early. Okay, as you can see here in my diagram, we have this bridge. This is exactly that I want to show you in my demonstration. So how we can create this bridge between our system architecture, our system engineering development to our design. Okay, how we can feed and make sure it's everything is correct. We are on a good path. This is the message. Okay, good. So let's talk about the digital thread. So a digital thread, I don't know if you know, but is a concept, of using software tools throughout the life cycle of a system to trace exactly the interconnections, of your data and software artifacts. So the, this digital thread is often a set of metadata, okay, that stores information about the system artifacts and their relationships. This is very important. And why digital threads are useful? So you can make this question is value, okay? So using a digital thread provides an advantage for product lifecycle management, okay? And what are the benefits of using digital threads? So you can track the change to artifact. You can trace the relationship between the artifacts, identify outdated results, and of course, perform incremental updates in results. Okay, so we are talking about traceability. Everything is connected. Okay. I have our first quick question. I would love to receive your quick questions by chat. My colleagues from application engineer, they are there. And in the end, we can discuss, okay, if you want to open your mic. But my quick question is, how do you manage your requirements today? Which platform are you currently using? Do you need any help to connect your requirement? So please share with us. Probably you are using Microsoft, Excel, Word, what else? IBM, engineering requirements, doors. What else? Polarion, JAMA. How could you share with us by chat? So we can see here a digital thread across the engineering lifecycle. Okay, what you're talking about. It links requirements to architecture, design, to code generation. If you need to generate C, C++, or if you need to integrate with another language, so this is important, Test and validation, your verification validation process, operational scenarios, okay, traceability and maintain throughout of the life cycle, okay. The flow basically ensures that change is one stage propagate across of others, okay. We can say enabling consistency, validation, and efficient management of systems variant. Okay. So an approach to validating and verifying system development is a V model. Let me know if you know this. It's a very common approach. The V model provides the development and verification framework, simple like that, but for model-based system engineering. So we are using model-based, okay? And I need to talk about model-based design. So we are talking about the V cycle. I need to talk about model-based design. Is part of this workflow, right? And it's fully supported by MathWorks in this case. So Fernanda, I'm looking only this part, the unit test. So we can use the MathWorks tools to do this unit test. Fernanda, I want to manage my requirements. I want to analyze these. I want to have traceability based on my requirements. So we can support as well. Okay. In summary, in the left side, you have the left side of the V identifies the steps that lead to code generation, including system specification, detailed software design, okay? And the right side, the V focus on the verification and validation of the steps, okay? So it's including software and system integration, okay? We'll talk about software in the loop that verify the component source code so you can execute the platform development based on your computer. Process in the loop, that the simulation on the embedded hardware, so you can verify the component object code, execute based on the platform target in the hardware, okay? And of course, the hardware in the loop. So this is a very common as well. So you can verify the system functionality and execute the platform and target in the hardware, okay? So just one note here. So model-based system engineering is a method, okay? Digital engineering is a broader ecosystem and strategy, okay? So as you can see here, this is another way to identify model-based system engineering process. So we are looking to a system requirement. We are looking to our algorithms. We are testing. We are doing simulations, analysis. We need to implement a specific, generate code, implement a specific microcontroller. And all the time that you were simulate, you were testing. You can see here, you are testing. Fernanda, I changed my algorithm. Let's run and test again. Okay, I'm changing the analysis. I want to see and change the options to simulate. Every time that you change something, you are testing. Okay, and then you integrate. Okay, this is the idea to use the model based. Okay, in our system engineering, our digital engineering. We have another quick question here. So, did you perform a testing in your workflow? So, when do you perform testing? And what is, how can I say, what is your biggest challenge to generate this test? Please share with me by chat. In the end, we can discuss later. Share, please. Okay, so you're using hardware-based testing. Fernanda, I have only hardware and test everything in the hardware. This is a manual, so I have a kind of Frankenstein. I know this is not good, but this is the way it's possible, to do it. So I have part from different team, and I have another team share their data, and then we can combine everything. This is a kind of test. Unit tests, so you have a model-based testing in unit test, or you are not testing, so you want to test. Let me know. Share by chat, please. I cannot see the chat now, but in the end, I'll see. Let's talk about managing complex projects. So why set up a project? Why set up a project? So setting up projects, especially in aerospace and defense, is not just about paperwork or process. It's what allows a highly complex and high-stakes systems to actually function in the real world, right? We start with a simple file, and then you increase the way that you are simulate. You have more people engaged in the same project. Projects provide a structure, right, that turns the connection into something practical and executable. So how to manage this? How to manage these files in a big team? So how do you do today? And I have this exactly quick question. So share by chat. Quick answer. Quick question, quick answer. So how do you manage all your files and folders? So do you have a specific framework to control how Or if you are a manager, if you are leading a team, tell me how does it work in your team? How do you manage the complex projects, the files, the team together? Source control. Do any of these sound familiar? One challenge we hear frequently, it works on my computer, but not on my colleagues. There could be many causes of this. So we hear, did you make a copy of your code? So you may yourself copy your code. So we have many, how can I say, versions, the final, the V1, V2, V3, and then we have final underscore final, right? So why you use source control in this first place? So this is a good way to manage this, right? So if you experience any of this, or if you are working on a project that has grown large over time, and you are, finding it more difficult to manage it, this is where the first advantage to track changes, encode, okay, collaborate more easily and avoid losing work. So I believe you get familiar with this this option with source control, but this is very important. It's totally connect with MATLAB. I will show quickly how to clone, how to commit, and how to connect with your files. Okay? You can see advantage to use source control with your MATLAB and Simulink modules. Okay, so MathWorks has a tool for effective teamwork. Okay, so you can label or classify files. Okay, so you can see the owners, you can see the names, you can classify, you can see which folder, which model in this case is connected with my Git. Okay. What else? What do you have? You can resolve merges conflicts. Imagine, so you have something that's not good, so how we can merge this conflict, how we can resolve these merge conflicts, okay? Easily view the changes highlighted in the models. So how you can see my colleague changed something in the code or in Simulink model, and what is the difference between the previous one? Okay, so you can see easily, you can see by, in this case, we're using a Simulink, of course, but you can see in MATLAB as well. What is the difference? Okay, share, reuse, and upgrade your project's file. So you can identify as well the impact of the dependent of a specific file. Okay, what is missing, identify if it's missing a file or something wrong. Okay, so you have, this is a good way to visualize the dependency. Okay. And of course, you have this option. Fernanda, I have very mature, project management. Everything is connected. My team, I have 20 people working this project. So you can integrate your CI systems such as, what is the name? Jenkins, your GitLab, GitHub Actions, and Azure DevOps. Okay. So this is a way that you can always, make sure it's everything going well. Okay. I don't know if you know. If you are interested to know a specific, process, Fernanda, I want to see more about this. Let us know. Okay, we'll be happy to share research or to set up a meeting. What do you have here? This is important. I want to show you. Modeling distributed simulation architecture. Fernanda, we're talking about, model, files, manage project, source control. But if you look, the end-to-end workflow of a distributed simulation. So to help, MathWorks has been working with many customers on a framework for their mission model development workflow. Okay, and how we can distribute this simulation. So we can start on the left side, So you have asset modeler who designed the Simulink component model in accordance with the actor level requirements. Okay, the actor can be the user, and the final user can be a specific person integrated of the project. And second, we have an integrator who assembles the actor, okay, model and publish into a repository. Okay, continue on that on the right side, something called a mission director. So we retrieve this actor model from the library and deploys them onto computers. Call it, we used to call always, the part of the environment. Okay, this director can also send commands into the simulation, such as reparametrizing something in the asset. Okay, and the environment reports out the status of the simulation for visualization or offline analysis as well. Okay, this is important because we talk about many steps of this workflow, the best practice. But if you look for a big workflow, how we can manage this is one option as well. And modeling this system architecture, here's a graphic representation of the framework. Okay, in the top right, you can see asset for the actor development environment, using Simulink, System Composer, and all the system architecture tools. So leveraging source control like Git and CI pipeline, okay, you can streamline and automate this development process, as well the ability to publish those products to a set library or its left. Okay, so we can then dynamically deploy actors into this world of simulations. Okay, you can then high and low fidelity visualizations to help access to the missions and the additional to offline analysis data. Okay, I have another quick question. Please share with me by chat. Okay, do you integrate the source control in your workflow? Are you using or running CI? GitHub, GitLab, SVN, Jenkins, are you doing this? Please share with me. Talk about the System Composer. I don't know if you know this tool, but System Composer is a platform for model-based system engineering, okay, at MathWorks. So it has all the functionality you would expect it from model-based system engineering tool, such as ability to create a composition diagrams, extend modeling elements with stereotypes and properties we will show you, and how to define the component interface. So you can module everything in terms of system architecture, okay? And then don't forget, you can create this bridge between system architecture and your designs. Okay, so you can see here we talk about satellite, we talk about aircraft, UAVs. You can combine different domains. Okay. So now, before to speak about our demo, before to go into our demonstration, our main demonstration, I want to show Fernanda how can we start with digital thread approach in my workflow. You can say to me, Fernanda, I am very advanced MATLAB user, MATLAB and Simulink user. Or I am beginner, Fernanda, I'm totally new in MATLAB and Simulink. How we can start use this approach in my system development workflow, okay? I record this quick video. You can see here how we can set up from scratch, okay? Here, decide to create my project, everything is blank. You can see I create my project. Now I want to connect with my source control. So I want to clone the Git repository. Okay, I clone easily with right click and my project, you already connect. You can see a new tab, project. Okay, so you can see now a new column. Okay, so how to commit easily by button in your MATLAB interface. Okay, so you can see here we connect all the files inside of my repository. Okay, now let's open Simulink. I want to create from scratch a system architecture. Okay, let's create our system. This system is my model. This is the name that I created. So now I will save quickly. What do you have in our system? We have components. right? So let's start with our component. It can be ground station. It can be satellite. It's a different team, okay? And I have another team working UAV with drones, okay? And I have another team working at ground vehicles, okay? So as we can see, we have different components, okay? And the last one, it can be hardware, software, visualization. How to connect? Simple. If you are using Simulink, it's intuitive, okay? Just to show you the options. Now, we are talking about the system requirements, system architecture, but how we can add behavior inside of my components, because we have design. We need to add intelligence behind of, the control, what this component is, okay? So in this case, I create Simulink environment, add a simple, transfer function and integrator. So you can see the symbol in Simulink. Now you create state flow. If you know state flow, if you don't know state flow, it's a tool focused in state machine logic. Okay, you can see it's very intuitive. We have states, different states, and inside of this state we have a condition. We have literally a condition that I need to move. Okay, just to show the options. Okay, we can go back, save, and then we can see our system architecture, models, design. Now let's start using requirements management. So you can see it's blanket. So you can start from scratch creating your requirements using MATLAB and Simulink. Okay, you adding one by one. Okay, manually. You can write. I open the requirements editor, and then you can add some details about this requirement. So you can see here my name, if it's a functional, what type of requirement we talk about. I add here control, now speed. So you can define, okay, let's refresh. But if you're having just a quick stop, so if you have already requirements and doors, RecIF, okay, JAMA, Polarion, any other tool that you can export, Prevision, so you can import to MATLAB as well, okay? But if you have this common, doors, Word, Excel, you can import easily. It's part of the... So I have separated some requirements in Word. I quickly import. You have some options to set up. If you don't need, just import. Let me know if you know this functionality in MATLAB, if you're aware about this. This is very interesting. That's exactly that I want to connect to our session. We want to create this digital thread. We want to create this bridge between our design and system development. We want traceability, okay? That's it. We are linking now. I'm just drag and drop the requirements. Is there other options? Right click and you can select the requirements, okay? This is a easy way to do drag and drop. So we have our system architecture, we have our design, we have linked. So you can see here all these requirements that are already linked, okay? So implemented. After to add your requirements, we can looking for your test. Okay, we have Simulink Test Manager, and then you have options to work with and create test case, test scenarios, okay? You can ask me, that's it to finish, okay? Sorry, what type of test do you have available in Simulink and MATLAB in general? So we have all this type of testing, okay? It depends your need, your needs, it depends of what exactly you want to do, to test, okay? If you're interested, again, please let me know. We can arrange a meeting. We can discuss later. Okay. Now let's go through our demo. Okay. Let me, instead of open this presentation, let me open my Simulink. Okay. Just a quick note, I'm using 26A, the version. Okay, if you were interested to run model modify this example, I can share with you. Okay, this model. What do you have here? As you can see, this is my system architecture. Okay, and inside of my system architecture, we have the ground control. Okay, this is a component. So you can see here we have requirements and we have Simulink. Let's open. So the ground control station basically is a component responsible for sending custom operator commands to a vehicle and operation. Okay, so we have options on ground, takeoff, landing, emergency. Okay, so if you go back, this is our main component. Okay, why? Because we have our ground control station, but this is the logic, this is the control. Okay, this is our quadcopter, our drone. Okay, so what do you have? This component receives operator from ground station and provides the UAV states. Okay, let's open this. What you can see, the air vehicle, let me, now is better. The air vehicle component consists of two components. So you can see we have subcomponents, the flight control and the vehicle model, okay, which process the operator commands and input to provide a UAV state as output, okay. So you can see here in my flight control, it's very important. This is our brain of vehicle, air vehicle. Okay, so we have model logic component that determines and implements the quadcopter mode based on the operator command. We have guidance that determines the relative position from the waypoints in the UAV state, and the feedback control. Okay, so this feedback control component basically is outputs the control command to a vehicle model or a quadcopter for processing. Okay, so these components receive the control from the commands and provide the UAV visualization. Let's go back to our visualization. So what we can see here, sorry, I forgot. So we have this big how can I say, big block, okay? The visualization component, you can visualize, literally visualize, okay, your quadcopter following predefined waypoints. This is the key idea, okay? So you are receiving the UAV state data, okay, from this that component, and animating in a quadcopter of 3D animation, okay? Let me double click. So what do you have available? We have a number of UAV, in this case I choose one. So you have UAV type, but you have fixed wing. Okay, this is a multi-rotor. So you have size, you have mesh color, so you can change the color. You have the trajectory, okay? So you have details about the numbers of trajectories. Okay, let's close and let's run. Let's see what we can see in this simulation. Where is my, sorry. Now they start following the waypoints, okay? Of course, they are following these waypoints on my axis X, Y, and Z, okay? This is my trajectory, and this first point is a little bit late, but then we can follow easily to the points, okay? It's going well. Okay, no issues so far. Almost there. And the quadcopter finally, let's see, lands. Okay, lands on the ground level. Perfect. Good. That's it. So you can see this is a simple simple demonstration, okay, about model-based system engineering. How the end-to-end workflow, how to verify, verify no, because I didn't show you the test, but how we can simulate your system architecture based on the control and design. Okay, now I want to show you how the requirements are linked. Okay, so how we can open our requirements. Let me close and open again. Apps, requirements. Okay, so you can see here all the requirements available. Okay, let me show some of them. So you have many options. Okay, so this is the requirements editor. Okay, so you can see all these details. But I want to show you how Simulink understand the test. Okay, so this is a test case. He's using a specific requirements. Okay, this requirement. Okay, this specific requirement. If you click here, exactly this one, it's linked and verify. Why is verified? Because I already run. Okay, I already run this test. But the idea to use the test is to verify one specific requirement, my system architecture model, and to use a specific criteria. Okay, I want to make sure if my drone, my quadcopter is following exactly this tolerance. Okay, I tested everything, I test verify it, and I have the results. Okay, so it's already passed. So you can see you have dashboards, everything the same environment. Okay, Fernanda, I want to generate report. It's possible to generate report. So you have based on the results. Okay, so you have all these details based on the results. I don't know if is it good to visualize. I think it's better. Okay, and you have the test specification. So this is another way to report, to generate report. Okay, so you have introduction. Everything here is automatically. Okay, everything, I mean the generate report. Okay, so you have a quick introduction about your model, the specification, the custom criteria that you use it. Okay, and the coverage settings. So this is the how can I say, the test manager. Okay, I don't know if I spoke so fast, but let me open my OPA. Let me swap. Okay, so this is in summary. I want to summarize everything. Connected digital thread transforms model, okay, into a single source of engineering truth, and model-based design enables faster and traceable and more reliable system development. We have some customer stories if you're interested.